Hello everyone. In this video, I'm going to drive the work-energy theorem. Work-energy theorem of electrodynamics. This theorem is also known as Poynting Theorem. And I'm also going to discuss the concept of Poynting vector. So there is going to be a derivation of work-energy theorem of electrodynamics or Poynting theorem. And I'm going to discuss the concept of Poynting vector. Let's start with the overview and goal of the problem that we are going to solve. Here we want to show that curly u by curly t plus del dot s equals minus E dot j. This equation is known as Poynting theorem or work-energy theorem of electrodynamics. From this equation, we want to show that the electromagnetic field obeys energy conservation law of this form of this equation. Here U represents the electromagnetic energy density. Here U represents electromagnetic energy density. S represents Poynting vector or energy flux. Poynting vector or energy flux. This E is the electric field and J is the current density. In this equation, the term on the right side, E dot J. This E dot J tells us how fast energy is being transferred. How fast energy is being transferred from electromagnetic field to charged particles. Or how fast energy is being transferred from charged particles to electromagnetic field. So this is a brief overview of the problem that we are going to discuss, the equation that we are going to drive, and the meaning of the equation. Now let's move towards the steps in order to drive this equation. The most important thing that you have to remember in this is that this is the equation that we want to drive, so that you can understand the steps that I'm going to do. So the very first step is you need to know the Maxwell's equations. The four Maxwell's equations are very important that are used in electrodynamics. In this problem, we are going to use only two Maxwell's equations. The first one is del cross E you can write these arrows on the vectors. Whenever you're writing the vectors in dot product or cross product, mark the arrowheads on the vectors. Del cross E equals minus curly B by curly T. This Maxwell's equations is known as Faraday's law. This equation explains that a time-varying magnetic field produces an electric field. The second equation that we are going to drive the Poynting theorem is another Maxwell's equations which is del cross B equals mu naught J plus mu naught epsilon naught curly E by curly T. Here, mu naught and epsilon naught, these are constants. Mu naught is the permeability of free space. This mu naught is permeability. While epsilon naught is permittivity. So we are going to use these two equations in order to in order to drive the Poynting theorem or work-energy theorem of electrodynamics. Next, we are going to take the dot product of these equations. You can remember that in this equation, this is the Faraday's law, and here on the left-hand side, there is E. So we take the dot product of this equation with B. E is the electric field and B is the magnetic field. This equation's dot product will be taken with magnetic field, and the dot product of this equation will be taken with electric field. This second equation is known as Ampere-Maxwell law. And so I can write this equation is known as Ampere-Maxwell law. It means that currents and time varying electric field produce a magnetic field. Our next step is we will take the dot product of this equation with E. So let's do that. From Ampere-Maxwell law, we know that del cross B equals mu naught J plus mu naught epsilon naught curly E by curly T, right? This is Ampere-Maxwell law or Maxwell's equations. Now we will take its dot product with E. This dot product becomes equals E dot J, and here it will become E dot curly E by curly T. This is our third step. Next step is that you need to know the vector identity. There is a vector identity which can be written as del dot E cross B. This E is the electric field and this B is the magnetic field. Del dot E cross B equals, this B will be written at start, B dot, now del cross E. And we will minus the term, we will use the minus sign next, and this E will come at start, E dot and del cross B. This is a vector identity. Here we need to find out the value of this E dot del cross B. In the previous equation, we have used this equation, right? Here is E dot del cross B. And in this term, in vector identity, there is also E dot del cross B. So we will get the value of E dot del cross B from this vector identity as, by arranging this equation, E dot del cross B. When this value is taken on the left side, this negative sign becomes positive. So it becomes equal to B dot del cross E Now, when this term goes to the right hand side, the positive sign becomes negative. So minus del dot E cross B. From this, we get that E dot del cross B. So from these equations, we see that the left-hand side of this equation and this equation is same. It means that the right-hand side of these equations will also be same. We will do that in the later step. Let's first substitute the Faraday's law. The very first equation that I wrote in Maxwell's equations, the Faraday's law, which was del cross E. Del cross E equals minus curly B by curly T. So when we take its dot product, now we take the dot product of this equation with magnetic field. So B dot del cross E equals B dot curly B by curly T minus B dot curly B by T. And here we know that there is B dot del cross E, and this B dot del cross E equals minus curly B by curly T. Therefore, this equation, by putting the value of B dot del cross B in this equation, we get E dot del cross B equals minus B dot curly B by curly T minus del dot E cross B. Now we will equate the two equations. E dot del cross B, the equation that we are going to equate is this one. Let's name this equation as equation 2. And this equation, let's name it as equation 1. So from equating equation 1 and 2, we get mu naught E dot J plus mu naught epsilon naught E dot curly E by curly T is equal to minus B dot curly B by curly T minus del dot E cross B. Now we will divide this whole equation with mu naught, or we can take the value of this mu naught common and then take it to the right hand side. Either way, the equation becomes E dot J plus epsilon naught E dot curly E by curly T is equal to minus 1 by mu naught into B dot curly B by curly T minus 1 by mu naught del dot E cross B. Now let's recall the very first equation that we needed to solve, that we wanted to drive. The equation was the equation that we wanted to drive, or the equation that represents the Poynting theorem, is given by curly U by curly T plus del dot S is equal to minus E dot J. Here we have E dot J. And this term 1 by mu naught into E cross B, this represents the S Poynting vector. But we don't know, we have not derived the value of U yet. So this U is given by U is equal to 1 by 2 into epsilon naught E square plus 1 by 2 mu naught into B square. Here this E is given by E dot E, and this B can be written as B dot B. Now, but we need, in order to derive the Poynting theorem, we need the value of curly U by curly T. So we will take the time derivative of this equation. The time derivative of this equation can be written as curly U by curly T is equal to curly by curly T into the first term of this equation 1 by 2 epsilon naught E square plus curly by curly T into the second term of this equation. So it is 1 by 2 mu naught into B square. Here 1 by 2 into epsilon naught is a constant. So it will be written as it is. And the time derivative of this term can be written as, this 2 will come at the start, the power will come at the start, 2 into E into the derivative of E. So 2E curly E by curly T plus here 1 by 2 mu naught is a constant. So it will be written as it is. And the derivative of B square can be written as 2B dot curly B by curly T. Here this 2 and this 2 cancels. On this side too, this 2 and this 2 also cancels. So we get epsilon naught E dot curly E by curly T plus 1 by mu naught into B dot curly B by curly T. This is the value of curly U by curly T. From here, we know that we can see that from this equation, curly by curly T into 1 by 2 epsilon naught E square is equal to this term, epsilon naught E dot curly E by curly T. While curly by curly T into 1 by 2 mu naught into B square, this term is equal to 1 by mu naught into B dot curly B by curly T. By putting this value into the previous equation that we derived, into this one, let's name this equation as equation number 3. Okay. By putting the value of value in this equation, here we have epsilon naught. Let's rewrite this equation. Actually, let's rewrite this equation. E dot J E dot J plus epsilon naught E dot curly E by curly T is equal to minus 1 by mu naught b dot curly b by curly t minus 1 by mu naught into del dot E cross B. This was our third equation, and in this we will write the value of here. This E dot curly E by curly T is equal to curly by curly T into 1 by 2 epsilon naught E square, and this 1 by mu naught into B dot curly B by curly T. This these two terms are the same, and this term is equal to this point. So we can write this equation as E dot J plus this term equals curly by curly T into curly by curly T into 1 by 2 epsilon naught E square is equal to minus, and this term equals curly by curly T into 1 by 2 mu naught into B square minus, this term will be written as it is, one by mu naught into del dot E cross B. So we have E dot J, and this we will arrange this equation to get the value of curly U by curly T, and we also has Poynting vector S. By rearranging this equation, we will take this value E dot J on the right hand side, and this will become negative, and we will arrange it in a way that the time derivatives will become together. So let's arrange this equation and rewrite as curly by curly T into 1 by 2 epsilon naught E square, and when this value comes on the right, it becomes on the left, it becomes positive, and this curly by curly T is common, so we will write it first, and in the bracket we will write 1 by 2 mu naught into B square is equal to sorry, this value will also come on the left side, so it becomes positive, plus 1 by mu naught into del dot E cross B is equal to when this E dot J is taken on the right, it becomes minus E dot J. From here, this value, we know that this is equal to U, energy density. So we can write it curly by curly T into this U plus this 1 by mu naught into E cross B. This equals S. So we can write it, this del will be written as it is, del dot S. This value equals S is equal to minus E dot J. This is the equation that we had to drive. This is the equation that we had to drive. The Poynting theorem or the work-energy theorem of electrodynamics. Let's revise the steps. What we did in order to drive this equation. Let's recall all the steps. At start, we did an overview of the problem that we had to drive this equation, curly u by curly t plus del dot s equals minus E dot j. Here S is the energy flux or Poynting vector. U is the electromagnetic energy density. And the term E dot j tells us how fast energy is transferred from electromagnetic field to the charged particles, or how fast energy is transferred from charged particles to electromagnetic field. Then we started our derivation. We started the derivation by using Maxwell's equations. We used these two Maxwell's equations to drive the Poynting theorem or work-energy theorem of electrodynamics. The first equation that we used was Faraday's law, which is given by del cross E equals minus curly B by curly T. The second equation, it is also Maxwell's equations, and it is called Ampere-Maxwell law. This equals del cross B equals mu naught J plus mu naught epsilon naught curly E by curly T. After that, we took the dot product of this equation with E and the dot product of this equation with B. Let me write it here so that you can recall. The dot product of this equation was taken with B, right? B dot. I'm only writing it so that you can remember it later. And the dot product of this equation was taken with E. E dot. Next, we use this value. We wrote this value. Let's do it. Let's take a look at it. Okay. Here we got the dot product of this equation with E, right? E dot del cross B equals this value. Then we used a vector identity. Which is given by del dot E cross B equals B comes at the start, B dot del cross E minus. Now E comes at start, E dot del cross B. After that, we arrange this equation to get the value of E dot del cross B, because E dot del cross B is also equals this value when we take the dot product of the Ampere-Maxwell law. So from here we get the that the left hand side of these equations. Here we will find the value of this B dot del cross E by taking the dot product of first Maxwell equation with B. So the dot product of these two equations will be used in the vector identity. Second step, first step is using the Maxwell's equation. Second step is taking their dot products, and the third step is using the dot products into vector identity. Here we took the dot product, this dot product, and now put the value of this dot product into the vector identity. So the vector identity becomes this one, this equation 2. By equating the two equations, we get another equation, mu naught E dot J plus mu naught epsilon naught E dot curly E by curly T. Then we will take the mu naught common, and or we will divide this whole equation with mu naught. By doing that, we get a third equation. This is the third equation. Here we recall the value of we recall the very first equation that we had to drive. Here we know that we have this E dot J and we have the value of S, the Poynting vector. We have E dot J and we also have the value of this Poynting vector, but we have to drive this curly U by curly T. So we recall the value of this U, energy density, is given by this equation. So we will take the time derivative of this equation. And by doing that, we get curly epsilon naught E dot curly E by curly T plus 1 by epsilon naught B dot curly 1 by mu naught B dot curly B by curly T. So we will put this value into equation number 3. Let's rewrite. We rewrite this equation as follows. Here we rewrite. Okay, we rewrite the same equation, and we know that from this derivation that this epsilon naught E dot curly E by curly T is equal to this value. And similarly, this value is equal to curly by curly T into B square by 2 mu naught. Then we arranged this equation and wrote the time derivatives together. These time derivatives together to get this value. Then we wrote this value curly by curly T as it is, and this is equal to the energy density U plus this del is written as it is, and this value is equal to S Poynting vector, and it equals minus E dot J, the same equation that we had to prove. This is the Poynting theorem. or work-energy theorem of electrodynamics. Now, this curly U by curly T represents the rate of change of energy. Rate of change of energy stored in electromagnetic fields. And this del dot S represents the net flow or divergence. This term, del dot S represents, the del dot S represents net flux, net flow, or divergence of electromagnetic energy. Divergence of electromagnetic energy out of a small volume. A positive divergence, if this divergence is positive, it means energy is leaving the volume. And this E dot J represents the work done per unit time. The term E dot J represents work done per unit time or power per unit volume. Power per unit volume. Power per unit volume or work done per unit work done per unit time by the field on the charges. If this E dot J is greater than 0, it means that energy is being transferred from field to the charges. There are two cases. This E dot J is greater than 0. In this case, the energy is being transferred from field to the charges, while the other case is E dot J less than 0. In this case, energy is being added to the field. So this was the Poynting theorem, and Poynting theorem is a statement of energy conservation for electromagnetic fields. This is all about today's lecture on Poynting theorem. If you have any questions about it, you can ask in the comment section. If you like the video, if you like this video, subscribe our channel and click the bell icon. And if you have any feedback, you can give it in the comment section. You can give your suggestions for the improvement of the lectures in the comment section.